But it's a two-layer story, right? It's the water level, but it's also the sediment level that matters. And so you get huge stretches of what the former lake bed was that are now in this condition, which are these shallow areas that every once in a while they will get enough water to come back over it and then wash back out. And this shallowing of a large area of the lake is a big portion of the problem because evaporation is such an issue here, right? So the lake itself now is doubling down on its problem because it's filling in these shallower areas. They get shallow, thin water. Thin water wants to evaporate more. And so you build onto this cycle of a problem. You go from where you had stackable water that evaporated slowly off the top to a saucer of water that evaporates very quickly. And just like you're seeing in Tuttle, that material wants to find that thaw wag. There's a big section of it fills back the former river bank, the former river, and that's also where Tuttle is using the water injection dredge to move most of that material, right? But there's also a lot of material that comes in and forms in and changes the tributaries out there. And that material and those impacts, a lot of areas, Lake Houston is a great example, a lot of areas that have those kind of conditions actually exacerbate their flood control conditions because those tributaries were their release. And if they're filling up with material on the bottom, then they're stopping that flow from happening. And this one, this image, so Lake Mead doesn't have the same problem that Conowingo does. It does still have functioning capacity on the bottom, even though there is filling in. But that's because they built Lake Powell upstream to catch the material. So the answer in that case was another catchment basin to hold the sediment before it came down to the lake. I think it's the reason to put this up there is to show how much of that flat water there is out there, how much of it isn't in the former riverbed. In those areas could be areas where the reduction or the reshaping of these water bodies could be part of the solution. And I think that's one of the things we always have to think about. When it's not the footprint that existed when we built the dam that's important. It's the footprint we can live with going forward. It's the stasis that we can find, the equilibrium to work with, that we want to try to find and look forward to. All right. So management approaches, we've talked about all these. I just wanted to kind of put a couple of definitions to these, and then we'll talk about solutions at the end. Dredging. Lake dredging is not unheard of. It's very uncommon, but it's not unheard of. This is Granite Reef Dam in Phoenix. That dredge there that you're seeing in the picture is over 70 years old. Now there's a new one out there now. They bumped it up. But since their existence, they have committed to a dredging program because of the two benefits. One, removing the sediment and reducing the cost for their water treatment. But even more important, you can kind of see these kind of barges of green out there, right? Removing the vegetation and the nutrient load that they would receive otherwise is the other biggie. And so they've been basically dredging the same space, the same forebay, for 70 years on a continuous basis. You can see their offloading location is up there just a little bit past the pipeline. I mentioned earlier about umbilicals being used and sent out to so this is an electric dredge, so the electricity runs on that pipeline floating on top, material's dredged, and dredged material goes out the bottom pipeline. It's now a museum piece if anybody wants to, kind of geek out on dredges, which I personally do. Those levers, the gentleman that ran the dredge, his arms were like Popeye. I'm amazed. It's quite a bit of gear. But anyway, so that's dredging. Dredging happens. Dredging can be part of your consistent plan. You need to be thoughtful. You need to think about where you can do it efficiently. You need to think about all the ramifications we've been discussing. Sluicing, we had that definition brought up earlier. So the difference between sluicing and flushing, and I think this is kind of the two terms that we kind of want to get separated here. Sluicing, you're going to have the infrastructure as part of what you've created. You have to have this gate or opening, weir structure, some sort, to release this water down. In general, when we're talking about flushing, we're talking about removing most of the water, if not all of the water, dropping it down and bringing down that water level. So, dredging, sluicing, flushing. I think, okay, probably good. We talked about it a lot. I didn't want to get into too much more. And then there's my favorite, bypassing. So these are the tubes at Tuttle Creek. It's always been bypassing sediments, right? Just not very efficiently. The water injection dredge is helping that happen much more efficiently by bringing that sediment to the tubes to be discharged. But that's a case of bypassing. So the point of this topic is to then say, okay, blue sky optimization, we are going to build a brand new dam, building it in a location. We want to be thinking sediment forward. We want to understand what that circumstance needs to look like, how we make these things happen. I will point out, and I don't know if our folks from Puerto Rico are here. Yeah, they are. That this was a designer who brought this to the client. And the design team was the one that was interested in seeing sedimentation being taken as part of the overall design and integrating it. We need a lot more designers and engineers and folks, saying, hey, these are things that will give you a more longer life to that dam that you're creating, will allow it to be more resilient, will allow it to function better. So it fits in the bypassing mostly conversation, but you'll see a little bit of each in the discussion of Rio Valenciano. All these schematics are at the 60% design level. This is based on a value engineering program. I was part of the owner's review on that 60% plan. They're all at a different angle, so I've tried to keep this blue arrow. Hey, that's where the water goes, so to keep you kind of oriented. So we're looking at from being in the lake, future lake, right? Seeing the structure below and the dam facility as it goes. So that area there is where I'm going to spend the most time talking about, and that is a turbidity current siphon that's designed in this. So you've heard about turbidity current when we've been talking about Tuttle and how the material passes through and down to the gates to get released. This will be done by a siphon. So imagine you've got that material on the bottom, floating, sediment, water, comes to the dam. The siphon is under pressure, and you'll see some images from the angle that'll give you a better demonstration of that, because the head is higher than that siphon outreach. And so it constantly is pulling this bottom water off the bottom, which is hopefully heavy with sediments. So the design this isn't conceptual, it's being tested I'm jumping to the next slide, I may not do that just yet. Hydraulic performance and sediment routing is part of the testing, evaluating turbidity venting and bypass. And then this is a picture of part of the physical modeling that's going on at Colorado State University. I think I got it right, Colorado State? Yeah. Almost forgot there. I almost said Kansas State. That would be wrong. Enhanced sediment and debris management. That's another interesting thing that we haven't talked too much about in the last day and a half. But debris is huge in dealing with reservoirs and your reservoir options, and understanding how and where you can handle these sediments. And each of these reservoirs should have both a sediment component removal and also a debris removal plan involved. And sometimes the debris removal plan will kill a lot of your sediment options if you're not taking care of it or doing it in such a manner ahead of time. This would be one of those places. The debris is definitely a large issue in the valley in Puerto Rico and all the things that are happening here. So part of the design had to be cognizant of how that debris could be caught, pulled off stream, off stem, I should say, and so the still water flow could maintain. So again, now we're looking at, so that's the siphon, so the bottom, that tower is on the back end, and the water is coming in, going up, and then out those piano weirs. I guess one other element to add to this design is not for water quality, and it's not for water storage. Mainly, water storage mainly for the pump station. It is not a water quality issue in that case, I think. All right, so sluice gates are built in. There are events in Puerto Rico, and I think it was mentioned at one of the slides during the presentation that was given. It's these huge storm events that bring most of the flow, water, and debris and sediment down. So it is a large event stipulation. So having these gates that you can open during those events and bypassing that material is super important. But you'll notice it's right next to this siphon that's constantly removing the sediment instead. So you've got this mix of we can handle the big pulses of sediment and we can handle the continual pulses of sediment. So the purpose of this paper when I was presenting it to the Western Dredging Association is we're doing a journal article for them in terms of looking at what the stasis is, what's the status out there in the dredging industry and reservoir dredging and in all of these great things. I'm just going to put a plug in here for water injection dredging. That is actually also taking off. So to date, there's been one operable dredge, and that's the North Carolina State Port Authority, and it operates continuously. It's the only dredge they're using. It's a water injection dredge. On my books already, I have 2 other demonstration projects that folks are looking forward to moving forward for, and it's because of projects like this. It's because of the traction that people are seeing. They're seeing these ideas being tested. They're understanding where the parameters are, and they are moving forward. One of those is in San Francisco Bay. And if you can get something permitted in San Francisco Bay, you can get it permitted in Kansas, I promise. That's the way to go. And the other one is for a port in Tampa Bay, that isn't going to use this to flush the material down and keep it continually moving. They're interested in using water injection dredging to level the sediments that are in their channel because they get peak shoals and it blocks the rest of the navigation channel. If they can come out and get these peak shoals down below, they can extend the period of their dredging projects, save money on the demob costs that they would have to have, and pay for this program to make it work. So there's some innovative ideas out there, and it's because people are willing to test these things. And so it's super important, and every time I come to one of these events, I really want to applaud the folks at the Corps and the folks at the Kansas Water Office for pushing this. This is not easy. This is not simple. This is not something that happens and just happens all over the place. And it's worth keeping that in mind. All right, so putting things together. Talked about dredging. That's the physical removal. You're severing sediments off the bottom somehow. Where it gets transported, how it gets transported, that's part of the magic. Sluicing, releasing a lot of this large amount of water and sediments at the same time. Flushing tends to be talking about bringing it down, bringing the whole system down. Worked on Lake Lure in North Carolina recently on the planning for that project's rehab after the hurricanes they had with Lean. That was a huge issue, that drawing that water down, getting access to. Debris was it was unbelievable, the amount of material that had to be removed that would be classified as debris opposed to sediment. Bypassing. If you can do this with the water's power to carry the material to carry out the mission of the river, this is the most efficient in general. It's the one that makes the most sense, but you got to get people comfortable with the concept. And then there are a lot of these hybrid strategies. So, we talked about out west in Lake Mead. Part of their strategy needs to be reconfiguring that basin, understanding that allowing a lot of shallow water isn't helping them. And maybe their dredging is just moving and recreating that basin so it stays deeper. Most of the area gets reduced. So area to volume of water gets reduced as a ratio, or depth to And then I just kind of, again, this is based on what we're going to put in the report. Then wanted to look at this as a function risk, sediment behavior, site constraints, and owner needs to kind of lay out a guideline. How do you go about tackling one of these things? What steps should you take? What things should you be aware of? What data should you be collecting? And that's that. Left him speechless. Yes. So Loiza, the dam that they talked about, does that on a regular basis. So there is channelized flow to keep most of the dense current going, but it's not being siphoned over. It's in the river to the reservoir system itself, yes. Let me see if I can do this. So in concept, basically having a conduit where you could pipe the material through the dam wall. Just so happens when you generally build the dam, one of the things you have to do is deal with that water coming to the dam during the time. And there almost always is a conduit or a section that's part of these dams. In this case, the conduit here would be close to the, which I don't know, have a pointer here, but to upper and to the left. That is one of the discussion points, and it's a great question, because that sediment doesn't immediately get to the dam to bypass, right? And so part of that plan is a sump and pump ability, or what part of the evaluation was, or the value engineering was, where you would catch the sediment upstream, use this conduit instead of filling it in, which is generally what happens after you build the reservoir dam, and be able to send material through that way. So you would do your dredging, pump the material down, and then bypass the section of the dam. So another way to bypass it with directional flow, that could be something like hydrosuction could be one of the things that would be used. It could be a regular dredge. Yeah, absolutely. And shoot. And think if you had planned it where you had one sump where you're planning to get the finer material, further up's a little coarser material, further up maybe the cobble material, whatever it is, and you send downstream a mixture of that sediment. One of the impacts of a new dam is you starve structures and infrastructures downstream of sediment. There are a lot of bridges and structures down there downstream of this that would be in concern. But keeping that sedimentation going, keeping that flow would be a way to avoid that. And it's it's the natural system. It wants to carry that material there. Hmm. Yep. Right. Yeah. No. Yep. Yeah. Yes, sir. The same happens, it's the same equation as you do for the sluice gate removal, right? It is whatever removal of water you do at that dam, right, has an impact upstream. So The answer, the answer to the question is that it's the same for anything that you're doing with releasing material through the dam. You're the same, I think, if I'm understanding your question correctly. It is down, it's down, so on that, on what you're seeing right there, the spill, the piano keys, that's on the outside face of the dam. So that's why the blue arrow is pointing in that direction. The lake is behind it, and the water is flowing through in that direction. In those cases, those gates would open if you were doing sluicing, but constantly, as we were talking, the stream of fine sediments is going through the chimney that's down there towards the bottom left, that help below the arrow. They're not doing hydropower in this case. Yeah, that's a good, no, I got you now, okay, yeah. Yeah, no. Now, could they, on a section of the dam, have removed one of the sluice gates and kept hydropower on maybe on the other side? Possibly, but then that wasn't the mission here. No, I got you. Yes, ma'am. I don't know that that happened in this case. I think that they kept the same capacity, but theoretically, you could, right? Because these are all oversized. It's like when I do dredging for navigation, I dredge to the bottom. If I just stop at the bottom depth that I want, immediately it starts filling in. There's always an over dredge depth. There's always an over capacity to a reservoir. Yeah, that's a yeah, we didn't bring that up in our value engineering evaluation, like, hey, let's make it smaller now instead. We were pretty excited about the sediment management portion of it, so we didn't think about that. But that's a real question to be asked, right? If we get more efficient at these systems, if bypassing becomes a regular thing, maybe it's a lot of smaller check dams that we're doing and not a large giant dam instead. You know, all possible part of the options if sediment is part of the original design. If it's always part of where you're thinking, if you're sediment forward in your design. Yeah, that's a good question. Anybody else? Yeah?